Hello everyone, my name is Aish Bisoy, and now from today we'll be learning about the chapters in grade 9. So the first chapter in our grade 9 maths textbook is number systems. And in the number systems we'll be learning what are number systems. Then we'll be learning real numbers. Under real numbers we'll be learning rational numbers, integers, whole number, natural number as a recap, and irrational numbers. So real numbers is a group of rational and irrational numbers. And what is number systems? Number system is a system of numbers, which means real numbers. Under real numbers, we have already learned rational numbers, integers, whole numbers, and natural numbers. This year, we'll be learning irrational numbers and what are real numbers. So let's move forward and we'll see. So let's have a quick recap on what we have learned. So we have learned natural numbers, which means 1 till infinity. Whole number means the inclusion of 0 into the group of whole natural numbers. Integers is the addition of negative numbers and positive numbers and 0. And rational numbers in the last is any number in the form of p by q, where q is not equal to 0. Example 3 by 4, negative 2 by 3, 4 by 5, 2 by 7, etc. Now moving forward, we'll be seeing what are irrational numbers. So now let's see what are irrational numbers. As the name says, irrational numbers complete the opposite of rational numbers. Rational numbers is any number which can be shown in the form of p by q. Irrational number is any number which cannot be shown in the form of p by q. For example, take any number to be s, which cannot be shown in the form of p by q, where p and q are integers and q is not equal to 0. So irrational number is any rational number which cannot be shown in the form of p by q. We will be seeing some examples. For example, we can take root 2, root 3, pi, 0.100110, any number like this. We can keep on showing. So these are some of the examples of irrational numbers. Now we'll be moving forward. So now we have seen what are rational numbers and what are irrational numbers. So what is a collection of irrational and rational numbers? When we see a number line, now we can only find out two types of numbers on a number line, either a rational number or an irrational number. So when we put the collection of rational and irrational number together, we call them real numbers. So any number on a number line is a real number, and it can be either rational number or irrational number. So for example, we can take a number line, and normally when we show them the number line, we put here like this. So here we can see that each of them are a rational number. But here when we move forward, we'll see how to plot irrational numbers on a number line, which is also possible. So we can summarize that every real number has a unique point on the number line. Also, every unique point on a number line represents a unique real number. Like for example, this point on a real number on a number line shows 0, which is a real number. This point on a number line shows -1, which is a real number. Likewise, every unique point on a number line will only represent a unique real number. Now we'll be moving forward and seeing how to plot irrational numbers on the number line. Now let's move forward and see how to represent irrational number on a number line. For example, take this to be a number line. Take a point O. This O can also be called as 0, and take one unit gap. That one unit can be either 1 centimeter or 1 inch, and mark a point called A. So here we'll draw a perpendicular. A perpendicular line will give us a straight line, and we'll cut like here. So here we get a perpendicular. When we join it, we'll find the point A. So this is a perpendicular bisector, which means this is 90 degrees. From there, we will take you again a unit length. You can see 1 centimeter. Like how here we took 1 centimeter, 1 inch. Here we'll be taking the same. For example, you took 1 inch over here. You will take one more inch over here. So here you can join from O to B. So this will give a right angle triangle. Using the Pythagoras theorem, we can see OB square. That means this line OB square equals to OA square plus AB square. Using Pythagoras theorem. So OB square equals to 1 square plus 1 square. OB equals to root of 1 square plus 1 square, that is root 2. So this length you see over here, this length is equal to root 2. This is root 2 units. This is root 2 inch. So you keep your compass needle over here, a compass needle and a pencil over here, and cut an arc over here. And this point is root 2 on the number line. Again, you take a point on a number line called O. Then 1 unit length from O, you mark a point called A. You construct a perpendicular bisector on A, and then you take 1 unit length on A. You get a point called B. You connect O to B. This length is called the root 2. Using similar methods, you can find root 3 also. And likewise, you have to just use the Pythagoras theorem. You have to see now here, root 2 equals to root of 1 square plus 1 square. Likewise, you need to find some numbers which will give you root 3 if you're plotting root 3. And using the same method, you have to construct and you have to cut an arc on number line to get root 2. Now let's see another example. Now take an example of root 5. So here again using Pythagoras theorem, we can see that 2 square plus 1 square is 4 plus 1, that is 5. And when we take the square root, other side it becomes root 5. So that means you have to take one side of 2 unit length and another 1 unit length. So here we do 2 unit length. Again, unit length can be of any unit, for example inch, centimeter, etc. And this side will be 1. So again we will take O as a point in the number line. Then we will take 2 unit length and take a point called A. On A we will construct a perpendicular. On this perpendicular we will take 1 unit length and make a point called B. When you connect O to B, we get root 5. Why? Using Pythagoras theorem, 2 square plus 1 square is 5, and when you take square to the other side, it becomes root 5. So this is root 5. Again, we keep our compass needle on O and a pencil on B and construct an arc. So we get a point called C. This is root 5. This is how we used to construct any type of irrational number. Now we'll move forward. Okay. So our next topic is decimal expansion. As we have seen, every real number can be shown in a decimal expansion. If we take a rational number can be shown in the form of p by q, which means they can be converted to the decimal expansion as well. And even an irrational number can be shown in a decimal expansion. And this is a very important way of recognizing a rational and irrational number. For example, the first type of decimal expansion is terminating decimal expansion. Terminating decimal expansion is any decimal which stops after a particular number of decimal places. For example, 0.5. 0.5 finishes after 1 decimal place, that is 5, and it is 1 by 2. Next is 0.875. We can see that the decimal stops after 3 decimal places, and it is 7 by 8. Next is non-terminating recurring. This means that the decimal does not finish. It keeps on going endlessly, but it has a recurring. The decimal repeats itself. For example, 3.3333. It will keep on going endlessly. That's why we put a bar. This bar over here shows that the particular digit is repeating itself. Here we can see that bar is upon 3, which means the 3 is continuously repeating itself, and this is 3 in its p by q form, it is 3 by 10. Next, the last decimal expansion is non-terminating non-recurring. This decimal expansion does not stop and also does not repeat itself, such as 0.100100. It can be any number, and this is an irrational number. We cannot convert this into a p by q form. So here terminating decimal is rational number, it's rational. Non-terminating recurring is also rational, but non-terminating non-recurring is irrational number. So likewise, we can classify the decimal into rational and irrational based on the two criteria we have seen. First criteria is if the decimal stops after some decimal places. For example, terminating decimal. The second one is on repeating. If the decimal keeps repeating itself, then it's a non-terminating recurring decimal, which is a rational number. And if it does not repeat, it's a non-terminating non-recurring decimal, which is irrational number. Now question arises, how do we write a non-terminating recurring decimal in the P by Q form? We know that this decimal does not end, but it keeps repeating itself. So we know it's a rational number. Now how do we write this in the P by Q form? So using the algebraic basics that we have studied, we will be taking x to be 3.333, the number given, that is 3.333. It's a bar because it's a repeating decimal. So now we'll take 10x. We multiply both the sides by 10, so we get 33.3 bar. So when we see this, we got two equations right now. X equals to 3.3 bar and 10x, which equals to 33.3 bar. So now we'll be subtracting them. We subtract this in order to cancel the decimals. We can see here the decimals are equal. So to cancel out the decimals, we do this. So that means 9x equals to 30. Now we take 9 to the other side. So it becomes x equals to 30 divided by 9. When we simplify, it becomes 10 by 3, which is the decimal, which is the P by Q form of 3.33 bar. So this is how we convert. So we take x to be the number given, then we multiply both the sides such that the decimal expand, both the numbers have the same decimal expansion. Here we multiply each side with 10. So we get 33.3 bar. Then when we subtract, you can see that both the numbers have the same decimal expansion. So we do this so that we can cancel decimal expansions out, and then we use, then it becomes 9x equals 30, and we take 9 to the other side, and when we simplify, we get the number 10 by 3. This is how we get this is what we do to get the P by Q form. Now let's take another example. Here the number is 0.235 bar. The bar is on 3 and 5, which means only 3 and 5 are going to repeat itself, not 2. So here there's a different twist. We take x to be the number given, and now this time we multiply it with x. Why x? Because there are 3 digits. Now we have to move this decimal 3 digits. So likewise we are going to do it with 100. Now when we multiply both the sides by 100, we get here 23.535, and it goes on. So here we are going to use a different method right now. So here we can see that 100x equals to 23.3 plus 0.23535. From where we get 0.23535? It is the same way. We can see that 23.3 plus this number gives us 23.535. And what is this number? 0.23535 is x. So which means 23.3 plus x. 100x equals to 23.3 plus x. And x is this number. So when we get a number like this, we can't directly subtract, because here this number is 2353535 and this is 535. So which means if you subtract also, it will be a different number. Likewise, we get here 23.3. So 23.3, when we take x to the other side, it becomes 99x equals to 23 23.3. Now here we have to remove the decimal. So to remove the decimal, we have to multiply it with 10, which means 9 equals to 23.3 by 23.3, which means 233 by 10. Now we take 99 to the other side. We get 233 by 990. This is the P by Q form of 0.235. Again, let's summarize up. X equals to the number given to us. Here, 2 is in the decimal, but it is not repeating itself. So we take 100. Now 100 we get 23.535. Here this is 535 and here is 235. We can see that both of them are not equal at all. So because of this, we try to separate the x figure out, that is 0.23535. There is an alternate method which I will be showing right now. We are using the way how we calculated the previous answer. The previous method that we are going to use here, the method that we use for finding the P by Q form of 3.333. Here, let's take a look. X equals to 0.235 bar, and here 100x equals to 23.53555. It will keep on going. So now here we subtract these both equations again as we did for the previous question. So 100x minus x equals to 99x. When you subtract this, we get 23.3. This is how we got it in the last time as well. Now again we can see that this equals to 233 by 10, which means x equals to 233 by 990. It is the same thing, but instead of taking the addition out, we are subtracting it. This might be a more easier method because this is how we used it in the previous question as well. So summarizing this method, we first take x to be the original number, then we multiply it with 100. So 100x equals to 23.535. Now we subtract them. After subtracting them, we only get one decimal digit left, that is 23.3. Then we multiply it with 10. If we multiply it with 10, we get 233. So when we divide 233 with 10, we get this number. So 23.3 can also be written as 233 by 10. Now when we take 99 to the other side, we get 233 by 990. This is how we use to find when there is an additional digit in the decimal place which is not repeating. Now we have learned how to find rational number between two rational numbers given. Now here we'll be finding irrational numbers between two rational numbers given. Here one rational number is 1 by 7. The value of 1 by 7 is 0.142857 bar, and 2 by 7 is 0.285714 bar. So for finding an irrational number, we know irrational number is a non-terminating, non-recurring decimal. So we have to find a non-terminating, non-recurring decimal in between these two values. We will get infinity such values. For example, we can take one as 0.150150000150. For example, this is just an example. This number keep on going. So this is one irrational number between the 1 by 7 and 2 by 7. Likewise, we can find many of them. Here you can see that the question asked to us is, we have to locate 3.36 on the number line. We have to find out 3.36 on a number line. So here 3.36 is a real number. So here we are learning how to locate a real number on a number line. So here first we see this value 3.36. So 3.36 lies between 3 and 4. So when we enlarge it, we can see here that between 3 and 4 we have 3.1, 3.2, 3.3, 3.4, 3.5, 3.6, 3.7, 3.8, 3.9 and 4. So here we know that 3.36 lies between 3.3 and 3.4. So we enlarge it further. On enlargement, we get to see the subdivision between 3.3 and 3.4. In between 3.3 and 3.4, we find out 3.36. This is the value that we need. So this process is called successive magnification. We consecutively magnify the number line until we find the number. This is in the case of a terminating decimal. When it comes to a non-terminating recurring decimal, it's a completely different way. It's the same method, but we can only find out the value till a given number of decimal places. We'll be seeing the next example. Here we can see that the question here given is we have to locate 2.7 bar on a number line, and it's given here find up to 3 decimal places, that is 2.777. So 2.7 lies between 2 and 3. So when we enlarge it, here we have 2 and we have 3. So when you enlarge it, we get 2.1, 2.2, 2.3, etc. So 2.777 lies between 2.7 and 2.8. That is here. We enlarge it more. So we get 2.71, 2.72, 2.73, etc. And we further enlarge it to get 2.777. 2.7777 lies between 2.77 and 2.78, as we can see over here. We further enlarge it, and after enlarging it we find a number here. This is a number. This is 2.777. It is not the perfect value because 2.7 root will keep on going, but because they are told to find the 3 decimal places, we only find the 3 decimal places and we get this 2.777. This is how we used to find it. So this is how we locate real number on a number line. Now let's move forward. Now let us learn how to mark the root of a decimal on a number line. Here, let the decimal be x. So the number here that we have to find the root of is x, root x. So first we will draw a line of length x, and we will mark one side as a and one side as b. So this is of x unit length. Then we take one extra centimeter. And mark the line as c. So a to c is of x plus 1 unit length. Here we take a and c as endpoints, and we find the perpendicular bisector. From finding the perpendicular bisector, when we connect it with the line, we get O. So O is the midpoint. It's the center of the line. Then as it is a center, we take the radius of OA and we cut an arc. So here we get a semicircle. Now when you connect B with a semicircle, we get and let the intersection be called D. So BD is of root x. How do we get that? Let us understand from the formula here. Again using Pythagoras theorem. Because what is radius? Radius is same throughout the circle. So OA, OC is same as OD because the radius is same from every angle, which means, for example, this radius is same, this is same, this is same, this is same. So radius is constant throughout the circle. So this means OD is the radius of the circle. So OD is equal to OC. OC is the radius over here, which is x plus 1 by 2. Why x plus 1? X plus 1 is a total length, and by 2, the x plus 1 is a diameter over here. Is a full straight line, and by 2 because diameter divided by 2 gives us the radius. Now OB is this length. We can see here that we have two values over here. One is OD and one is OB. What is OB? So if x plus 1 by 2 is this, then OB is x minus 1, because here this 1 is not included. OC is x plus 1, but OB is x minus 1. So x minus 1 by 2 is OB. So here when we substitute the values, we get BD. We are finding the value of this line over here. So BD square equals to x plus 1 by 2 square minus x minus 1 by 2 square. Using the identity we learned, that is a square plus 2ab plus b square. Using that formula, we get here x square plus 2x plus 1 minus 2x minus x square plus 2x minus 1. Here this should be minus and this should be plus, but because we have a sign over here, we multiply the sign, so the sign changes, and as it becomes like this: minus x square plus 2x minus 1. When we can x square and negative x square gets cancelled, plus 1 and negative 1 gets cancelled, so we get 4x by 4. Now 4 gets cancelled, we get x. So BD, when we take this square to the other side, we get root x. This is how we find the value of this. So BD here is root x. So we keep the compass needle on B and take the radius of BD and cut an arc. So here we get point E. Point E is the length of root x. This is how we find. With an example, we will understand how to do this better. Okay, with this example, you will be able to understand this more better. Now, we have to find root 4.5 on a number line. So, first we take a line of length 4.5 with endpoints A and B. We extend it further with one more unit length C. So here AC is going to be our diameter. So here we have to make arcs which cut each other, and then we get O, which is the midpoint. This is the perpendicular bisector. We get O. With O we make a semicircle, and then we connect B to the semicircle on a point called D. This line is of length root 4.5, and then we keep our compass needle on B and our pencil on D, and we take and cut an arc. We get the point E. This is going to be root 4.5. This is how we mark the root of a decimal on a number line. Now, how do we add or subtract the values of a irrational number? Here we can see the question is 3 root 5 plus 2 root 7 as one value, plus 5 root 7 minus root 5. Here we can see that it is commutable, which means we can interchange the values. So when we interchange, we normally tend to bring the like. Like means here you can see that both of them have the same root values, that is root 5. So when we take it together, it becomes 3 root 5 minus root 5, which gives us 2 root 5, and 2 into root 7 plus 5 into root 7, we get 7 root 7. So we just add them and keep it like this. We can't simplify it more. So here we could simplify it because there were numbers with the same root forms. But if there is no number with the same root, like root 5 over here or root 7, then we just keep it as it is, like this. Now let's move and see what do we do in multiplication and division. Here we have two examples on two different situations. Your first situation we see, again the roots, we have two same numbers as the roots. Example here is root 3. So we just normally multiply all the 4 terms given here. 6 into 4 into root 3 into root 3. Root 3 into root 3 will give us 3, because root 3 into root 3 means root 3 square, which means 3. So we multiply them normally and we get the answer 72. Here we can see that here it's root 5 and here it's root 2, which means they cannot cancel out each other. So when we multiply, it becomes 3 into 2 into root 5 into root 2, which means 3 into 2 is 6, and 6 into root 5 is 6 root 5, into root 2 is 6 root 10. So that's the value over here. This is how we multiply. Now let's see how do we divide. Okay, let's get a look on this. So it is 5 into root 20 divided by 2 into root 5. So here we write 20 into its factorized forms. So here we get 5 into root 2 into 2 into 5. We can see here it's 2 into 2, which means 2 square. So that means root of 2 square, which is root of 4, is equals to 2. So that means 2 comes out. So after 2 comes out, they get multiplied. So it becomes 10 into root 5. So it is 10 into root 5 divided by 2 root 5, which means they get cancelled, and we get the answer is 5. Again here, whenever we get such type of questions, we should normally separate the numbers into their prime factors. So here when we separate into prime factors, we get it as 2 into 2. So root of 2 into 2 is equals to 2. So 2 comes out of the root form and it gets multiplied with 5. So it gets 10 root 5, and down here 2 root 5. So it gets cancelled, and the answer comes out to be 5. Here are a set of identities which we will be using even in the root forms. So we have learned the algebraic identities. So here you can see the 3, 4 and 5. These are the identity, I mean third and fifth one are the identities. First one is root A, root B. Here there is no other root, it's only a square root symbol. If for example here it was cube root, then it would be different case. But then here it is only root, which means it is square root. So square root A and square root B will be square root AB. So likewise, root A, root B will be root A by B. So they'll get common. Now third one is the identity. The third identity we learned last year. That is A plus B into A minus B is A square minus B square. So here root A plus root B into root A minus root B equals to root A square minus root B square. So here, because they have been squared, the root gets cancelled and it becomes A minus B. Here this is a multiplication of a monomial with a monomial. Binomial with a binomial that we learned last year. So here C first gets multiplied with A, then C gets multiplied with B, then D gets multiplied with A, then D gets multiplied with B. So this is how we multiply a monomial with a monomial, and that's how we get root AC plus root BC plus root AD plus root DD. And last one is the A plus B whole square formula here, which means A square plus 2AB plus B square. So here again, because the root has been squared, the root gets cancelled out, then 2 plus, here we can see again root A into root B. So using the first identity, we get 2 root AB plus B square, because again the root gets cancelled out. This is how we use the identities for the root numbers, which have a root symbol, or also called as radicals. Normally, when we are given a question to solve, we cannot leave the denominator in a root form, because it is not the standard form for fraction. So we have to take this root form to numerator, not to the denominator. For this, we multiply number with its conjugate. Conjugate means, for example, if we have a number like a plus root b, the conjugate of a plus root b is a minus root b. The symbol in between the two values change, not the value in front of it. For example, it will remain the same. The value in between the two numbers change, so that's called a conjugate. For example, here it's 1 by a plus root b. So here we have to multiply it with its multiply and divide it with its conjugate, so that it remains same. So here we have to multiply it a minus root b by a minus root b. So here using the identity we learned, so we will be doing a plus root b, a minus root b. So here we will get a square minus root b square, which is equal to a square minus b. So here we will get the answer as a square minus root b by a square minus b. So this is what we get after rationalizing it. This is called rationalizing the denominator. So in this we see that normally we cannot leave the denominator in a root form. We have to multiply and divide it with its conjugate. So that the numerator becomes into root form and the denominator is left with a rational number. Let's take an example. Now we have been given a number that is 2 minus root 5 by 2 plus root 5. So first we have to rationalize it. For rationalizing, we will multiply and divide it with its conjugate. So it becomes 2 into root 5 by 2 into root 5. So we get it as 2 minus root 5 square. We'll use the identity minus the other identity that we have learned. So here it will be 2 plus root 5 into 2 minus root 5. So using the identities as we learned, it will be 2 square, 2 square which is 4 minus 2 into 2 into root 5. So it will be 4 root 5 plus root 5 square, that is 5, divided by, using the identity, we will get 2 square minus 5, and 2 square here means 4. So here we get it as 9 minus 4 root 5 by negative 1, which means negative to take into the top side will be this 9 plus 4 root 5, sorry, 4 root 5. Here we have negative 1 in denominator. Now we also, as we have learned last year, we cannot leave, according to the standard rule of rational numbers, we cannot leave the denominator in a negative number with a negative number. So the negative will go to the up, so it will become, we'll multiply both the sides with negative 1. So likewise we will get the answer is 9 plus 4 root 5. This is how we rationalize. Here again we can see that here we have to use identities. That's why I have told that identities are very important for rationalization, and with that even multiplication. So here we can see 2 minus root 5 by 2 plus root 5, we multiply it conjugate. Using the identities we solve the first part, and then even we solve the denominator, and that's how we get the answer is 9 plus 4 root 5. So we have learned the laws of exponents. Now here we'll be learning how a number can get integral power, and how a number can get even a real number as its power. First we will reflection with the ideas of laws of exponents for natural powers. For example, a power which will be a natural number. So according to that, a to the power m into a to the power n, we'll be adding the power. If the base is the same and they are being multiplied, we'll be adding their powers. If the bases are same and we are dividing their powers, then we'll be subtracting the powers. Then if there are two powers, a to the power m to the whole power n, then we'll be multiplying those two powers. And then the next one is, if there are two different base but with the same power, so we'll be multiplying the bases together. Now, and any number to the power 0 is equals to 1, and a to the power any negative number, then we have 1 by a to the power m. This is for if the power is to natural number or an integer. Now we'll be moving forward and seeing what will happen if the power is any rational number. Those are called integral powers. So this is called the extended loss of exponent, or the loss of exponent for a number with integral power. Integral power here means it can be either be a negative power or fractional powers. For example, here let p and q, here we have p and q, let this p and q be any rational number. So when we multiply, this is the same identity, same law as before. We are going to add the powers if the bases are same. And next one is the same, if the bases are same, then the powers are going to get subtracted. Next one is, if there are two powers, then we are going to multiply them. Then the next one is, if the powers are the same but the bases are different, we'll be multiplying the bases. And this a to the power a negative p, then it is 1 by a to the power p. And this is the last, is the most important that we are going to learn, that is a to the power m by n. Here we see here it's a fractional power. So when it will be equal to nth root a into m, equals to n root a m. This is the most important law that we're going to learn when we have a fractional power. The n goes as an nth root, and then we have m. For example, look here. We have a question 64 to the power 1 by 2. Here we can solve it in two methods. First method is, as we have learned, 64 2, and this is gonna be 1. So it will be square root of 64, which is 8. Another method is 64 to the power 1 by 2 can also be written as 64 can also be written as 8 square. So 8 square to the power 1 by 2. As we have learnt, a to the power m into n, we will be multiplying the two powers. So it will be 8 into 2 into 1 by 2 equals to 8. These are two methods of how to find out. The first one, we use the integral power formula, according to which the numerator stays as it is as a power, but this the denominator goes as a root. So here it becomes square root of 64, which is 8. The second one is using the factorial form. Here we factorize it. 64 can also be factorized to 8 square, and then we multiply the two powers. Here is the how we multiply and divide two numbers with fractional powers. Here the fractions are unlike terms, so we first make them like by finding the LCM and multiplying them, and then as normal subtraction subtract we sorry they should be 13, we add them. So when we add the powers here, we get 13 by 15, and then we can write it as I've said. The denominator comes here and the numerator stays as a power. So here it is 15 root 2 to the power 30. Here it's 11 to the power 1 by 2 by 11 divided by 11 to the power 1 by 4. Here it is subtraction. So first we have to make them like terms and then subtract. So here we get 11 to the power 1 by 4, which can be written as 4th root 11. So here our chapter ends. I hope you liked my video. If you liked it, then please click the like button, and if you have any queries or questions, you can ask in the comment section. Thank you.